And hi there, what we are doing today is going over division, and we're looking at the different manipulatives that we can use for explaining division, as well as the different techniques in explaining division. Here are the topics that we're going to cover in regard to division. We're almost to the end of Chapter 3. Once again, we're going to look at a few problems that will allow us to look at these different methods for introducing division. So you can pause your video here if you want to read through those, and I'll be discussing them. Notice how in problems 1 and 2 we have discrete items, which means they are countable items that we can divide into different groups or sets. In numbers 3 and 4 we have continuous items that are measured. So that's a little bit different and a little bit harder to look at. Let's first look at problems 1 and 2, and we will note that we can divide our classrooms so that we see how many Apple computers. I was thinking this was a pie question. It's not. This is the Apple computers. So we're going to divide our classrooms and figure out how many Apple computers. So what we could do, since we have 4 classrooms, I think, we can just start plopping our Apple computers in there until we reach the 24. After which we can go, oh, look at how many computers each classroom gets. This model is called a partitioning model because first we set up our groups and then we started plopping our little computers in there. Now for our apple problem, where we're making our apple pies, we are saying, okay, it's kind of like a subtractive model, because what we're doing is we're saying, okay, 4 apples for the first pie, another 4 apples, so 24 minus the 4, minus the 4, minus the 4. So we call that a repeative subtractive model for that particular division. So let's go over our terminology. Our number B, which would be the number right inside here, inside your division problem, that's going to be called the dividend, and it would always be your first one when written out horizontally. N, which is the number that's going into it, he's our divisor, he's the one that's on the outside, and our answer is called the quotient. So here is a table that gives those numbers with their correct terms. Once again, using our whole and part model, here we are looking at the repeated subtraction and the partitioning model using that same whole and part. Sometimes children are able to use the missing factor model, where they go 4 times what is 24, and that's a very effective way to think about division, as well as the number line model. But if you'll remember, the number line model is not one that they have found statistically that is best for students' learning, but it is one that reinforces students' learning. So you wouldn't want to use this when you were first introducing division. You might want to use it after you've already talked about division, and then it can make connections for students. Now this is not necessarily something for your students, but is definitely something for you to think about, the fact that the commutative property and the associative property do not hold for division. So what I mean by that is 12 divided by 6 is not the same as 6 divided by 12. So we don't have that same property list for division that we do for multiplication, and very similar to subtraction. Something that is at times confusing is the fact that we cannot divide by 0. Division by 0 is undefined. It's kind of like taking a cookie and trying to divide a cookie that is something physical into 0 parts. It just doesn't really make sense to divide something into 0 parts. And it doesn't work for our definition either, the way we have defined division. We defined it in terms of multiplication, so what times 0 will give us a number, and that's not possible. Represented in this slide is a scaffolding algorithm. It kind of shows why our place values are what they are in doing our division. Now here's a very common mistake that students will tend to do. When this student took the 6 and went into the 43, they chose 6, and that works. However, it would have gone one more time, and so we've got this big number that kind of makes a mess here. One of the things you'll need to tell students is when they subtract, this number down here always needs to be less than what you were dividing into. Otherwise, it could have gone one more time. And this slide is about good operation sense. I think, we're all striving to make sure our students have a good operation sense, a good understanding of everything that's going on with each of our different operations that we're choosing to talk to them about and trying to explain. So I think one of the best things that you can do in trying to make sure that they have this good operation sense is trying to approach all of your math from as many different angles as possible. These are fun little games for students once you teach them their different operations, just to see if they can figure these things out. It helps them just not do just a straight up kind of problem. They still are practicing their different multiplication, addition, subtraction, division facts. It's just kind of like a little puzzle, a little game, and students tend to enjoy this type of thing. So if I were to look at this one, you can piddle around with it. You're sitting there in your head going, okay, is that plus, minus, times? And eventually you should come to you might want to pause it if you want to figure it out, but you'll come to 6 times 5 is 30, and then divided by 3 is 10. And you can come up with a whole bunch of these. You just go ahead and write out your problems for your students, and then just replace your operations. You make out your key first, and then replace all the operations that you have written down with circles. Here's a little bit of explanation, or a couple of examples with terminology. We say that 3 is a factor of 12, 4 is also a factor of 12. We can say that 3 divides 12. We could say 2 divides 12, 6 divides 12, 4 divides 12, 12 even divides 12. It means that 3 divides 12 means it goes in evenly. Now we would not be able to say 12 divides 3, because then I would end up with a fraction, so that wouldn't work. 12 is divisible by 3 because it goes in evenly, and 12 is also a multiple of 3. If I were to write this down, I'm going to write, and I would say it just like this: 3 divides 12. That's what this symbolism represents. And it means that it goes in evenly. Remainder of 0. This is an interesting fact, and this is just kind of a game, or you might give this for extra credit for students, or even a problem where they would go through the different dates and try to figure out, okay, which one of these could I come up with a relationship to. It just gives practice, and has students do something other than 20 problems on a piece of paper. Divisibility rules are fun. 5 is one of the favorite ones because all the numbers that are divisible by 5 either have a 5 or a 0 at the end. Very cool. It's one of the first ones you learn. And this is that explanation using our base 10 blocks and just separating these things in 5s. 10 is another beautiful one. If it's divisible by 10, it's got a 0 at the end of it. Using our base 10 blocks, here we are looking at that. Is a number divisible by 2? Well, if it is, then it has one of these numbers at the back end, either a 2, 4, 6, 8, or a 0, because those numbers are even. Here is using that base 10 model for divisible by 2. Here's the base 10 model looking at divisible by 4. And then looking at it as divisible by 8. So let me go back to the 4 for just a second, because if I am looking at the divisible by 4, one of the tricks of this is, and you can see why when you analyze this a bit, if you look at the ones and the tens digits, if you look at those two digits and those two digits are divisible by 4, so this one 1232, it would definitely be divisible by 4 because the 32 is divisible by 4. Because we already know that the 1200 is. So then extending that, divisible by 8, we would look at the hundreds, tens, and ones position, and if 8 will go into 621, then we know that this big old whopping number is divisible by 8, so it makes it nice and easy to see if that is divisible. And I know that 8 won't go into 621 because of that 1 there at the back end. 3 is one of my favorite divisibility rules. If you sum up all the digits in your number and then you look at that sum, if that sum is divisible by 3, then your number is also divisible by 3. Similarly, this works for 9s as well. That's why the hand trick works, because when you bend one finger down, then you only have 9 fingers that you're playing with, and those two digits sum up to 9. Alright, well, this slide asks you to do a problem. We're talking about order of operations. Now, they're going to say whether or not you come up with two different answers is going to depend on whether or not you do order of operations, and many of our calculators today follow order of operations, but not all. So if you used a calculator that follows order of operations, like your TI 8384s, then you're probably going to get the correct answer for order of operations. But if you use a simpler calculator, it just depends on which one you use as to whether or not you'll get the same answer. And here they are kind of explaining that as well. So going over some of our divisibility rules for this one, let's look, if I can get my mouse over here, there we go. Let's look at some of the numbers that would make this true. If I add 3 plus 9 plus 6, that's going to give me, what, 12, 18. So it already is divisible by 3. It is divisible by 3, but I meant by 9. So I need to put a number in here that will continue to make it divisible by 9. So I could either plug in there a 0 or I could plug in a 9, and that sum will still be something that's divisible by 9. So let's look here. 3 plus 4 plus 3. That's what, 10. So I need to get to 12. So a 2 would work. I could get to 15 and that would work, so a 5 will work. And I could go to 18 and that would also work. So I'll plug an 8 in there. So any one of these numbers plugged into that slot would make that number divisible by 3. Next one is exactly the same. Oh, okay, well that was handy. Now I'll go to the 12. Now for something to be divisible by 12, it must be divisible by both 4 and 3. Those would be the easiest to look at. So let's look and see what we can do with this number. 4 plus 6 plus 8. That gives me 18. So that is already divisible by 3. So to make it 3 go into it, I could have it be 4, 6, 8, 0. I could make it 4, 6, 8, 3. That would work. And 4, whoops, and I'm getting writing off the page, sorry about that. 3 would go into 4, 6, 8, 6. That would work. And 3 will go into it as 4, 6, 8, 9. So I also want 4 to go into it because I'm looking at 12. So you're out, buddy, and you're out. Let's look and see which one of these will 4 go into. Well, I just look at these two back digits for a 4, and 4 goes into 80 but not 86. So this number there must be a 0. Can't be the 86 because 4 won't go into it. Okay, I'm going to let you watch me set this up. What I need to do is make this guy a little bigger because he is too small. So I just snipped it, and now I'm trying to make it go on the page. I usually go to Image, Canvas Color, make it white, and then I'll make sure I have this. I'm going to hit the delete key to get that dumb thing off there. Then I'll take this stuff and scoot it on over. And normally, if I'm making this for a class, what I usually do is kind of keep making it bigger until it really fits in the screen very nicely. But in this case, I'm wanting you guys to see parts of the screen, so I'm just not going to worry about it. So I go to my pen here, and I already have my pen set up on the width that I like. I usually like about this, and I get to choose any one of these colors, or I can choose any color I want. You can go to this color scheme here. I'll just choose the pink just for fun. And now I'm going to do some prime number stuff now that we looked at my Snagit. Alright, so 53, the definition of prime is any number other than 1 or any number greater than 1 such that 1 in itself will go into it, and that's the only two factors that it has. So what you have to do is just start testing some things, and so I look to see if any 3's will go into this. 5 plus 3 is 8, so no form of a 3, a 3, 6, or 9 will go into it. I know a 2 won't go into it. I know a 5 won't go into it because the back numbers aren't of the form that is needed. It's not a 5 or a 0. It's not an even number. So then I have to start testing some other kind of numbers. I have to start seeing what if some of my oddball numbers will go into it. So I start checking things like a 7, because I don't really have any good rules for 7. So I look to see if a 7 will go into it, and he won't, because 7 times 8 is 56, so that won't work. Then I look at 11, he won't work. A 13, that won't work. And then once I get up to halfway, then I can be done checking. So 13 won't work. Then I'll go to 17 because I'm checking other kind of oddball numbers, just not a normal one. And once you get up past your 29, then you're done checking, because after that then it would have had to have been doubled. So I'm going to say this one's prime, and unless you really check all of those numbers up until then, you don't really know for sure. This one I know happens to be composite because 5 goes into it, so I'll check that. 83, that's a pain in the butt because it's kind of a big number, and I have to do the same kind of thing that I did for 53. I'll have to start checking. I check my 3's, 8, 9, 10, 11, nope. No 2, no 4. I start checking 7, 11, 13, 17, and try to see is there something that'll go into it. Once I get up past 41, then I don't need to check anymore, and you will find that 83 is indeed prime. Alright, well that concludes this week's video. I hope you guys have fun, and if you have any questions, please email me. Alright, bye now.